In the previous lecture, we worked out the kinematics for special relativity. Essentially, we came up with the equation that the total energy squared of our system is equal to the momentum times the speed of light squared plus the rest mass times the speed of light squared quantity squared. Where if there is no momentum, the object is at rest, then what we get is the very familiar E is equal to mc squared, basically the rest energy. So now what I'm going to do is apply this to a couple of problems so that we can see how to use relativistic kinematics. So the first one we can look at is example 12.7, where we have two lumps of clay, lump 1 and lump 2, and they're coming at each other with some momentum. Let's say the speed of each of these is 3/5 the speed of light. So each lump is coming at the other one with the same speed. So this is the initial case. After the collision, they stick together into one big lump, and now that lump is at rest. So it has zero final velocity. And let's also say that they stick together to form a single mass, m. So initially, each of them has a mass, little m. Okay, so what we want to do is work out the conservation of energy and momentum. So before the collision, what we have is the total energy is gamma mc squared, and this is per lump of clay. Okay, so each of them has a relativistic energy of gamma mc squared. Now, gamma is 1 over 1 minus beta squared square root, or 1 over 1 minus v, which is 3/5 c divided by c, quantity squared, square root. And so in the end, what you get is 1 over the square root 1 minus 9/25, which in the end works out to be 25 minus 9 over 25 square root, all of that over 1, or essentially 5/4. Okay, so therefore the energy of each lump of clay is 5/4 mc squared, and I have to now add two of them because there are two lumps of clay. So if I add that together, I get 10/4 mc squared, or 2.5 mc squared. Now, we can take a look at this, and we can then set it equal to the final energy. So after the collision, F final squared is equal to 0 momentum, so it's not moving, it's at rest, plus mc squared quantity squared, or the final energy is equal to, mc squared. So if we set these two equal to each other, that initial energy is equal to the final energy, then we have 2.5 mc squared plus equal to capital M c squared. So that's canceled. So in the end, the total mass in the system is 2.5 times the mass of each individual lump of clay, which, non-relativistically speaking, if I take two lumps of clay and I add them together, then I should get 2 times the mass. But since these lumps of clay are moving at relativistic speeds of 3/4 the speed of light, 3/5 the speed of light, then that means that some of their energy was converted into mass. So it ends up with a larger mass um, because of the speeds of the collision than in the case where you just are moving at non-relativistic speeds. Okay, so let's take a look at another example. So let's take a look at, say, pion decay. So the pion is a subatomic particle, which I'm going to call pi, and it's sitting here at rest. So the initial case is our pion at rest, and then spontaneously it decays, and it'll decay into a muon and a neutrino particle. So it'll decay into these two particles, which now are moving away with some speed. So what we're saying is the mass of the pion is going to convert into the mass of the muon, the mass of the neutrino, and the momentum of the neutrino and the muon. So let's say before the decay, the initial case, what we have is the momentum before is 0, it's at rest, which means that the energy before is just the mass of the pion times c squared. Okay, so now let's take a look after the decay. So after the decay, what we have is a total vector, which I'm going to call b sub alpha. Now this alpha is an index, where alpha goes from 0, 1, 2, and 3, so time x, y, z. And that is actually the sum of two momentum vectors, I'll call c and d, where this is the muon vector, and this is the neutrino vector. So b is just this total vector. Okay, and so if I write this out, then c sub alpha is the energy of the muon, and then px of the muon, py of the muon, pz of the muon. And so I'm trying to keep this notation straight, so I'm putting the particles label inside the parentheses. D is the neutrino, so that's the energy of the neutrino, px of the neutrino, py of the neutrino, and pz of the neutrino, which means that my vector b is the sum of these terms. So basically, when you're adding these four vectors, you add each of the four vectors up individually, just like you would if you were dealing with orthogonal components. Okay, so what we do know is that conservation of momentum means that the momentum of the muon, the 3 vector of the momentum, px, py, pz, is going to be equal to minus the momentum of the neutrino, because they have to conserve momentum, so they're going to decay back to back from each other at 180 degrees. Conservation of energy says that the total energy of the muon plus the total energy of the neutrino is going to be equal to the total energy of the initial pion, which is just mc squared. Okay, now let's say the neutrino's total energy squared is its momentum times c squared plus its mass times c squared quantity squared. But it turns out the neutrino has a really, really small mass. It's like 1,000,000 times smaller than something like the muon. So we're going to assume that the neutrino has 0 mass, which means that the total energy of the neutrino is just the momentum of the neutrino times the speed of light. Okay, so the magnitude of the momentum of the neutrino should be equal to the magnitude of the muon from conservation of momentum, which means that this is now equal to the square root of the energy of the muon squared minus the mass of the muon, c squared quantity squared. Okay, so now let's put all this into our equation. So that means that the energy, so if we look at our conservation of energy equation, the energy of the muon plus the energy of the neutrino, which is just equal to the momentum of the neutrino. So we can write that in as the square root of E muon squared minus the mass of the muon times c squared squared is equal to the mass of the pion times c squared. Okay. And okay, so now let's write this out. Well, let's try and do some algebra. And so I should have E of the muon quantity squared minus the mass of the muon times c squared quantity squared is equal to the mass of the pion c squared minus the energy of the muon, and that whole thing squared, because I basically moved the energy of the muon to the right-hand side, and then I squared both sides to get rid of the square root. And when I do that, I get the energy of the muon quantity squared minus the mass squared of the muon times c to the fourth is equal to now the energy of the muon squared minus 2 energy of the muon times the mass of the pion c squared plus the mass of the pion squared c to the fourth. Okay, so if I look at this, I can cancel out the energy of the muon right there, and what I am now left with is, let's see, I can cancel a c squared out of both sides. So that becomes c squared, and so if I now want to solve for the energy, I have 2 times the energy of the muon times the mass of the pion is equal to the mass of the muon squared plus the mass of the pion squared, all of that times c squared. So I factored out the c squared, and so now if I divide by the mass of the pion, the energy of the muon should be equal to now the mass of the muon squared plus the mass of the pion squared times c squared divided by 2 times the mass of the pion. So since I know the masses of the muon and the pion, because I've measured them from previous experiments, I can now calculate exactly what the energy of the muon should be in the case where the pion decays at rest.